Okay, everyone, we're gonna start now. Welcome to the Paragon X EM class. Today is gonna be our eighth class of this 10-week class. So yeah, let's go over the homework from last week first. Remember, we learned about inductors, right? So first problem, the inductance of a closely packed coil of 400 turns is 8 microhenry. Calculate the magnetic flux through the coil when the current is 5 uh or sorry, millihenry and then 5 milliampere. Okay. So all right, we want to find the inductance. Well, okay, so we want to find okay, so we have the inductance, we want to find the flux. So let's recall how we defined the inductance, right? So we say the inductance L, that will equal to total number of turns, then times the flux, so the flux phi, and then divided by the current, right? This is just going to be simple algebra. We're given the inductance is 8.0 millihenry, so we'll say that 8.0 times 10 to the negative 6 uh Henry, right? Because that's microhenry. So equals to a total number of turns, which is 400. And then we're gonna say times the flux. So we want to find the flux and then divided by the current, right? So 5.0 times 10 to the negative 6 ampere. Okay, then from this, you can do the algebra. You can solve for the flux phi. So you'll find it's going to be, once you do the algebra, right? So it'll be, I believe, 10 to the negative 13th. Right, 10 to the negative 13 should go to your flux. And then times whatever units is needed. But yeah, so this problem, just remember how we define inductance. And then after that, plug in the numbers and it's just some simple algebra. So yeah. Let's move on. All right, here's a bit more interesting problem. So two toroidal solenoids are wounded around the same frame. Wounded, yeah. Solenoid one has 800 turns and solenoid two has 500 turns. When the current 7.23 ampere flows through solenoid one, average flux through each turn in solenoid two is 0.043. Uh, yeah, WB. That's just the units. All right, what's the mutual inductance of the system of the two solenoids? Okay, so mutual inductance, remember, in the last problem we talked about the self-inductance. Mutual inductance is a bit different. So remember, if we have yeah, so right now we're talking about two toroidal solenoids. Let's draw a picture first then. So this will be the the toroid that we wrap the solenoids around, and then so we have two of them, right? So maybe this is my first toroidal solenoid, something like that. All right. And my second one, let's draw in a different color. Maybe it will be like this. So solenoid two I'll draw a bit less dense because yeah, we'll let this one be solenoid two. So this is uh yeah. Yeah, so it's just two solenoids wounded around the same frame. Okay, and remember how we define mutual inductance, right? So if we have, for example, one solenoid, and I want to find how the change in the current or the change in the magnetic field produced by the first solenoid will affect the second solenoid, right? Because if I have uh, a current or like a magnetic field due to one solenoid, and that's changing, that leads to a change in flux through the second solenoid, and this in turn causes an EMF in the second solenoid due to the first solenoid. So that's why we call it mutual inductance, right? So let's say the mutual inductance, so on, well, in this case, we'll say on solenoid one by solenoid two, you'll find that they're actually equal, like all on solenoid two due to solenoid one, but let's say for now, on solenoid one due to solenoid two, well, we first want to find the flux due to solenoid two, right? That'll be number of turns through solenoid two, times times the flux, yeah, the flux due to 2 on to 1, right? And then divided by the total current through solenoid 1, right? Uh, that should be the number of turns through, right? Number of turns through solenoid 1 times the flux due to solenoid 2 on solenoid 1 and then divide by the current through solenoid 1, solenoid 2, right? Because we're looking at the effect that 2 has on 1. So, okay, what does this mean? Well, all right, we're given all the numbers here, right? So mutual inductance of the system. So solenoid 1, it has 800 turns. All right, and then solenoid 1, right? Okay, solenoid, yeah, solenoid. We're given solenoid 1's current, right? So 7.23 ampere. So we also know that this should equal to mutual inductance on 2 by 1, right? So that's also equal to number of turns through of 2 times the flux on solenoid 1 or by solenoid, yeah, by solenoid, oh, my bad. Should be flux on solenoid 2 due to solenoid 1. So, all right, I'll just change my subscript notation, sorry. All right, so on solenoid 2 due to solenoid 1 and divide by the current through solenoid 1, right? Now I'm given solenoid 2 has 500 turns, right? So this will just equal to 500 times the flux through each turn solenoid 2 is 0.043, so 0.043, and then divided by your current through solenoid 1, right? So 7.23. And then after this, you can just do some, yeah, just yeah, this is just what you get for the mutual inductance, right? So you can plug this into a calculator and you'll get your answer for mutual inductance of the system. And actually, you'll find that, mutual inductance of 1 due to 2 is equal to mutual inductance of 2 due to 1. So we'll just let this equal to the mutual inductance of the system. Yeah, so just remember how we define mutual inductance and you should be good. All right. When the current through solenoid 2 is 3.45 ampere, what's the average flux through each turn in solenoid 1? Okay, well, now we can use this over here, right? So assuming that you already plugged into a calculator and found what this is, right? I'll just let that equal to m. We know the value of m now, right? And now we know equals to that, right? Well, we're given solenoid 1 has 800 turns. Solenoid 1 has 800 turns, so we'll say m equals to 800 and then times the flux we want to find, right? So times flux uh through 1 due to 2 and then divide by current through 1, right? Current through solenoid 2, right? We're given is 3.45 ampere. So to do that, and then you can solve for flux 1, 2, and you'll get your answer for the second part of the problem, right? All right, now third part of the problem, in the new trial with the same solenoids, the current in solenoid 1 changes at the rate of 0.25 amperes per second. What is the induced EMF in solenoid 2? Well, okay, let's first erase my drill over here so we can get a clear screen. All right, so we're given the mutual inductance, right? We're given mutual inductance M, and then I'm given the current through solenoid 1 is changing at a rate of 0.25 amperes per second. What is induced EMF in solenoid 2? Well, I know that because like we learned this from mutual EMF, mutual inductance, right? So the EMF in solenoid 2 due to solenoid 1 would be equal to the mutual inductance times the I1 dot. And you can see like di1 over dt, right? And you can see it's really similar to what we had for the self-inductance, right? So remember, for self-inductance, we had E self equals to the self-inductance, L self, and then times like its own current, d of its own current over dt, right? So here it's just the same principle, right? We're getting it's equal to m times I1 dot, which is 0.25 amperes per second, right? So times 0.25, and after that, you'll get your answer for induced EMF in solenoid 2 due to solenoid 1. So yeah, that's how you do the three parts of the problem. Just remember, like overall, just remember how do we define mutual inductance, right? And yeah, once you have your definition of mutual inductance and also the like the induced EMF due to the mutual inductance, you should be able to solve all parts of these problem. Yeah, let's go on. Any questions on this part, by the way? If not, let's go on to the next problem. All right, two identical long wires of radius r equals 1 millimeter are parallel and carry identical currents in opposite directions. Their center to center separation is d equals 10 centimeters. Neglect the flux within the wires, but consider the flux in the region between the wires. What is the inductance per unit length of the wires? Okay, yeah, let's always draw a picture first. So, example, let's say this is my first wire, or actually, yeah, let's draw a top view first. So let's say like I have one over here, one wire over here, and another wire over here, right? And the wire on the left, it's carrying current into the screen, so I'll mark that by an X. And there's another wire that carries current out of the screen, so I'll mark it by a dot, right? And each of this, the radius is 1 millimeter, right? 1 millimeter. Okay. Their center to center separation is D equals 10 centimeters. So this would be 10 centimeters, right? 10 centimeters equal to D. Okay. Now neglect the flux within the wires. Consider the flux in the region between the wires. All right. So we want to look at the flux, right? So remember, if we want to find the flux, we want to find a magnetic field. So let's sort of review how like what's the magnetic field due to infinite long wires, right? So if I have one long wire, so let me draw a separate diagram. So this is one wire and say it's carrying current into the screen. Remember we found that you use your right hand rule and you can also use Ampere's law, and you'll find that the magnetic field would be running in circles. So something like this, there'll be concentric circles. These will be the magnetic field lines. And remember, we found that you found that B would equal to like B equals mu zero I divided by 2 pi r. And let's remember that the r over here, the r I write over here, it's not the radius of the wire, it's the distance from, it's like the distance from like the location you're looking at the field at to the center of the wire. So I'll say it's B as a function of r is equal to mu zero I divided by 2 pi r, right? Okay, so in this case, we want to find the flux in the region between the wires. So let's draw the magnetic field lines. Uh, so due to the left wire, it's going into the screen. So the magnetic field looks something like this, right? The concentric circles in this way. Let's go. Let's do another one. Oh, another one like this, right? Oh, other direction. And what about for the wire on the right? Well, now this one's going, the current's going in a different direction. It's coming out of the screen. So you know that the magnetic field line would look something like this. So be going like this, something like that, right? And okay, now if we want to find the total field in the region between the wires, right? So essentially what we're looking at is we're basically looking at this region over here, right? So over here, We want to find the flux in that region. Wait, how do we do that? Well, if I'm looking at this line over here, notice that along that line, the field due to both wires would actually be vertical, would be pointing downwards, right? So for example, if I look at yeah, if I look at maybe a point over, say over here, where the yellow dot is, the field due to the first, due to the wire on the left, it will be pointing in this direction, right? And then the field due to one on the right, it will also be pointing downwards. It'll have slightly larger magnitude because it's closer to the wire on the right, but overall, the total field is always vertical, right? So in general, let's express the field in the region between the wires, right? So I'll say that B total, B total would equal to, if I sum these two together, right, for both of the wires, will equal to mu zero, mu zero I, and then over 2 pi, and then times something in parentheses, right? So 1 over like some radius r, right? To let's say r to the left wire, right? And then plus 1 over d minus r. This will be the distance to the other wire, right? And then, so I want to find the flux, right? Well, what's the flux? Well, okay, if I want to find the flux in that region, right? So the field is pointing, the field total field is pointing like downwards, right? Meaning that if I want to find like an area to find the flux through, then I'll look at an area that has for example, let's say I set up the coordinate system so it's this is the x direction, this will be my y direction, it's my y direction, and into the screen will be my z direction. So there will be one into the screen, that will be in my z direction. So I want to find the flux in the xz direction, right? Because my field is in the y direction. So this is in the y cap direction. Actually, it's in the negative y cap direction, but that doesn't matter. So negative y cap direction, and then meaning that I want to find the flux through the xz plane. So that means if I want to find a d flux, right? So d flux would equal to what? D flux would equal to the B total times dx times dz, right? So it'll be uh mu zero. Okay, let's just write again, right? Mu zero times I divided by 2 pi. And then let's do 1 over r plus 1 over t minus r. This is in the y cap direction, so we dot onto the xz direction, and what will we get? We'll get times dx and times dz, right? Well, dz, you can also write it as dl of the wire, right? Because the wire is in the z direction, so we'll say dx dl, right? So this is our d flux. Now we want to find the total flux in the region between the wires per unit length, right? So we'll say d flux divided by, sorry, d flux divided by dl. So this is the flux per, the infinitesimal flux per unit length of the wire. Well, this will just cancel the dl on both sides, right? So then now I want to find the total flux in the region between the wires. So I'll do the integral of d flux, integral of d flux. Okay, and then will equal to, it will be equal to the integral of d flux, sorry, integral of d flux over dl, right? So we want to find, this will be equal to integral of mu zero I divided by 2 pi, and then times what? Times 1 over r, 1 divided by r, plus 1 over d minus r, and then times dx, right? Now, what are our integrating boundaries? You might be tempted to say from 0 to 10, but or like from 0 to d, right? Problem with that is that first off, if we do from 0 to d, we'll get like infinity, right? Because it's 1 over r and 1 over d minus r. Instead, remember we're given that the wire has like it has a radius, right? So it's slightly thick, meaning that our integral, our lower boundary and our upper boundary will not be from 0 to d, right? It will be from, if I say, yeah, this is, we're given it's small r. Well, let's equal to, let's say it's called d0, just to like not confuse the variables with like, my r over here and my r over here, right? Let's say it will be from, the upper boundary will be, d minus d0, and the lower boundary will be d0, right? Be from d0 to d minus d0. Once you do the integral, right? It's a pretty simple integral, so it will be equal to mu 0 I divided by 2 pi on the outside. What we're getting in the inside, well, we're going to be getting natural log of r, and then minus natural log of d minus r, right? So let's rewrite that as natural log of r over d minus r. And then our integrating boundaries will be from d0 to d minus d0. And in what we're, oh wait, so we're given like radius 1 millimeter and radius 10, radius is 1 millimeter, d is 10 centimeters. So I can rewrite my boundaries as d0 would be 1 millimeter, right? So I'll say, remember when you use SI units, so 0.001 meters, and then to d equals 10 centimeters, right? So that'll be 0.099, I believe. Yeah, 0.099 meters. And then you plug in what you know for mu 0 and 2 pi, right? That's just constants. Uh, Also, we assume we're given the current through each wire, and then you can just plug in 0.099 meters and 0.001 meters, and yeah, overall, that'll be your answer to the problem. That's the flux through unit length of the wire in the region between the wires. So basically, if I were to recap this, just remember that uh, yeah, so the superposition of the total magnetic field between the two wires is perfectly vertical, and so I can easily write what's the flux, right? So it'll just be the field total, the total field times dx dl, and we want to find flux, flux per unit length, right? So that dl cancels. After that, you just get an integral. Watch out for the integrating boundaries, and then you can easily get your final answer that way. So yeah, I know this was a big problem, so yeah, if you guys have any questions, we can talk about that. Just send a message in the chat. All right. In the meantime, let's move on to the next problem. Yeah, final problem. This shouldn't be too hard. A 12 Henry inductor carries a current of 2.0 ampere. At what rate must the current be changed to produce a 60-volt EMF in the inductor? Well, remember we have epsilon equals to Li dot, basically L di over dt, right? Now, what were we given here? Mm, yeah, we're given that L equals to 12 Henry. And yes, we are given that, oops, 12 Henry. And even though we're given that I equals 2.0 amperes, it's it's redundant information, because if we want to find the EMF, we only care about the change in the current. Because remember, we can have a current, but it won't cause any EMF, right? We'll only have an EMF when there's a change in the current, which causes a change in the flux, because changing current causes a change in the magnetic field, right? So what we'll do is just 60 volts equals to the inductance, which is 12, and then times what we want for di over dt, right? So I dot, meaning that we're getting that I dot would have to equal to, we'll have to change it at 5 amperes per second. And yeah, this is much simpler compared to the previous problem, but it just helps you remind you what's the definition of the EMF due to inductor. Make sure, like, don't get thrown off by like them giving you this information. Um, like you won't always have like the information given to you in problems won't always be necessary, right? Here the current, it doesn't matter. We only care about the change in current, and we're given epsilon, we're given inductance, so we can just easily solve for the I dot. And yeah, I believe that's the end of our homework review. I don't see any questions in the chat, so we can go on to the lesson. And yeah, Sean McDonough, tell us about DCRC and LRL circuits.
Yeah, so today we'll be learning about DC, RC, RL circuits. Next slide, please. So quick review. We know Ohm's law, V equals IR. Hope everybody knows that by now. Um, you should know like general, just drawing circuit diagrams is very helpful, right? You have your voltmeters, you have your, oh sorry, this is a battery, I think. Yeah, battery. You have your resistors, you have your capacitors. You have your inductors, and then yeah, resistors in series, remember we add them up. In parallel, we add the reciprocals and then take the reciprocal of that. In capacitors, it's the opposite. For series, we do the reciprocal thing, and for parallel, we just do simple addition. And for oh wait, one more. Yeah. And for inductors, it's important to remember that for inductors, we're gonna add. And if we're parallel, we're gonna do this. So inductors are very much like resistors. Yeah, next slide. So quick review problem. I think we're gonna skip number two for now, but try number one. Uh, yeah, I'll give you like 2 or 3 minutes. Yeah, so the general idea for this problem is basically we have our voltage, 1.3 kilovolts, and we have our resistors, right? So we want to find this. I will label this I2. We'll label this I1, and we'll label this I3. And basically, since like the actual like amount of resistors don't really matter, it's only matters what the equivalent resistance in each of these paths is. So we can find that the equivalent resistance of these pair is 100 plus 100 equals 200. And for this one, it's just one resistor, it's 100. For this one, we can use our parallel rule and we can use the series rule. And you're gonna get 150. And now, oh, and also another important thing is we have this another resistor. This we can say the current through this is I, and we know that I equals the sum I1 plus I2 plus I3 because they all join back over here and just go through the rest, right? And we know that I you can find I from your V and the overall resistance that can be calculated. So we know I. We also know the voltage. So we know this voltage, and then using I, we can do V minus I times R9. R9 is this resistor. So we can do V minus R9 equals the voltage is like this voltage, right? So if we have that voltage is simply the voltage from across this loop, across this loop, across this loop. And then we can simply use V equals IR again, and we can solve for all of these quantities. So yeah, I'm not gonna go through it because there's a lot of calculation and math, but that's a general idea. Um, this one, uh, the second problem, I'll let you think about this more. Hint, look for the voltage loops. Remember Kirchhoff's law, the sum of the voltages in a loop is zero. So try to find a loop that makes this, like the charge on C, very easy to calculate. So we'll come back to this later, yeah. All right, next slide. So DC circuits, first of all. DC means direct current. It'll have a battery and the battery provides a constant source of current. Or it's more like voltage. So if we have we have our battery. This is the symbol for battery. And it's a simple circuit. It doesn't have capacitors or inductors. We don't have those. Instead, we're just gonna have like resistors as we saw in the previous slide. And theoretically, these can have constant current forever, but physically, what's going to happen is that these resistors are going to heat up and they're going to dissipate energy and it'll decay over time. But for theoretical applications, we'll just consider this. And you can always represent them as only as one battery and a resistor, as I've drawn here. And yeah, just follow the Ohm law. Ohm's law will just be your guiding light, V equals IR. That's all you need to solve DC circuits. All right, yeah, next slide. And now we have our second type of circuit, RC circuits. So RC stands for resistor capacitor. So it's basically what I drew on the last slide is a circuit with a resistor, but now we're gonna put a capacitor. And yeah, I'll talk about the sometimes part later. So theoretically, this current will run forever, but it decays. It gets closer and closer to zero. The capacitor is initially so here we have our battery and we have our circuit here, right? So if I put this switch here to A, then it connects the circuit. And if this capacitor is initially uncharged, we're gonna have a current run through it, and that current, which you can solve for in the differential equation, we'll do that later. This current will cause the capacitor to gain charge, and the current will eventually decay to zero. But if the if the capacitor is initially charged, it'll lose if the capacitor is initially charged and we disconnect the battery, So we flip this switch to B. So we're just gonna have this loop. Then it'll lose the charge and eventually it'll decay to zero. So and importantly, to solve for these, we will use a voltage loop rule. Yeah, next slide. So yeah, now we're gonna try to find the function of a charge over time for a capacitor in an RC circuit without a battery and the capacitor is initially charged. So we have your R, you have your C. This is initially charged, and then we want to find the function for Q of T, which is the charge on the capacitor. All right, I'll let you guys try to work this out. But yeah, use this voltage loop rule. It's very important, and try to write a differential equation. Okay, I think we're gonna go over this because yeah, not much time. But basically, we're gonna say we have our current I going through this, and we're gonna write the voltage loop rule. So we're gonna say that IR, the voltage across the resistor, plus the voltage across the capacitor. Remember that Q equals CV is another important thing for capacitors. So we have Q over C. This is zero. Now, can you tell me how I'd write this as a differential equation? Maggie, can you tell me? Oh, sorry, this should be minus. My bad. Anybody can tell me how you can write this as a differential equation? That's fine. Remember this definition of current. I equals dq over dt. This is very important. This is a very important definition because um, because if we plug this in, if we plug this into here, we're gonna get that dq dt r equals q over c. So we can separate our variables and get rc. Wait, sorry. We can say that dq over q equals dt over rc. So this equation, you can integrate both sides. Now it's like calculus. And um, I'll use a different color. So the final thing you'll get, I won't like explicitly do it. We're gonna get that Q equals Q naught times E to the negative T over RC, where Q naught is like your original charge. Q naught is the original charge on the capacitor. So yeah, we can see that this is like a decay function, right? It'll decay to zero eventually. And another one last important thing is that a lot of textbooks usually define this time constant tau as tau equals RC. This is just good. You can just like substitute this in and like yeah, they just write it like that. All right. So are there any questions on that? All right, if not, next slide, please. All right. So yeah, we can uh for initially charged, we can like graph this on a graph. So we have this Q, a Q of the capacitor as a function of time. We can use our Q equals Q naught E to the negative T over tau. So as you can see, you get this function, which it's a decay function. And using I equals dq over dt, we can take the derivative of this with respect to time, this equation, and you will get also another decay function. You'll get q naught over tau times e to the negative t over tau. I'm dropping the minus sign because that doesn't matter for our purposes. It just depends on the direction you're in your notation. But yeah, you also get this decay function. Using V equals IR, you can write V equals Q naught R over tau times your decay function. So you're gonna get this decaying thing, right? So you can see all of these will be decay. Everything is gonna go to zero in this situation. Yeah, exponential decay. That's the important thing about discharging in an RC circuit. So next slide. Oh, are there any questions on that? Uh, all right, yeah, yeah. Next slide. So now we have our second case where we have an RC circuit, but the capacitor is initially uncharged. But now we're also connecting a battery. So the battery will force a current through it, and then we want to find the function of the charge over time for the capacitor in this case. So this is very similar to our first situation. If you write the voltage loop rule, you can write it as a differential equation and you will get the function. So I'll let you try that. Yeah, it's very similar to the first case. So yeah, I'll give you like 2 or 3 minutes. Yeah, I think we'll go over this now. So yeah, we're gonna write the voltage loop rule in the same exact way, except now we do have this this voltage E epsilon. We can say that epsilon minus IR, voltage across the resistor, minus Q over C, which is the voltage across the capacitor, equals 0. And we know that I equals dq dt. So if we combine these, so combining these, we can obtain a function for q. We can say that q of t, um q of t, sorry, q of t equals epsilon over RC, RC times 1 minus e to the negative t over RC. Again, you can use tau equals RC to write it in terms of tau if you find that easier. And from this, you can also obtain a expression for I of t, the function of the current as a function of time. And for this, you can get that I of t equals, um, um, I think you will get like I, or I kind of forgot, but you get, yeah, you get epsilon, uh, but yeah, you can do that. You'll get a function for I. I'll let you do that on your own. Are there any questions on that? If not, we can move on. Next slide, please. Yeah, and as we did before, we can graph the functions we got. You can see that the charge approaches asymptotically since it's a 1 minus a decaying function. It'll approach an asymptotic of c times epsilon. And if you take the derivative dq dt, you'll get the decaying function of the current. Um, and for the voltage, you'll voltage you can get a thing, and for resistor you can get a thing, right? For VC, you can just do Q over C. So you take this function and you divide it by C. And for the resistor's voltage, V equals IR, you can take this function and multiply it by R. And some of the start cases and end cases are very useful. A lot of problems would be like immediately as the switch is thrown, what is the current? Or a long time after the switch has been thrown, what is the current? So you can see that immediately after you connect it, the charge is 0 and the current is simply epsilon over R. But after a long time, the charge is C times epsilon and the current is 0. So in these two cases, you can see that immediately after the switch is thrown, the capacitor is simply like a wire. It just acts like a wire after a short time, but after a long time, it'll become like a short circuit. It'll be like an off switch after a long time. All right. Are there any questions about that? If not, I can go to the next slide. Yeah, so some examples to solidify the concepts. I'll give you 3 or 4 minutes to work on the first one. Yeah, I think we can go over this. So we have our function q of t equals c epsilon naught times 1 minus e to the negative t over r c. So we can simply plug in our numbers. 6 times 6 times 1 minus e to the negative 5, it's after 5 seconds, divided by RC, which is 6 times 3 is 18. And yeah, you can plug in these numbers and yeah. Any questions about that? I believe the answer you get is 8.73 coulombs. All right, and for the second problem, we have that the capacitor is charged for 5 seconds and then the battery is removed. How long will it take for half the charge to dissipate? So we can use our discharging equation. Q equals Q naught times e to the negative t over RC. And we want Q to equal half times Q naught because you want half of it to dissipate. So half times Q naught. And you can plug in these numbers. Um, and you can solve for t. You can get t. Are there any questions about that? All right. Next slide then. So the last circuit we're going to go over today, RL circuits. RL circuit stands for resistor and inductor. So basically we have an R, we have an L, and we connect our battery also, it provides our EMF. So basically after a short time, the inductor acts like an open switch. So at a very short time, it'll act like an open switch. Because remember, what do inductors do? They resist change. So as soon as you flip a switch that turns the circuit on, then it'll resist that change and it'll act like an open switch. So it won't let the current go through. But after a long time, it'll just act like a wire. It'll just be like a wire instead. The current will just be going steadily through. It's in a steady state. And to find the equation for the voltage as a function of time, we can apply the voltage loop rule again. So next slide, please. Lucas. Yeah. So we want to find the function of current over time in an RL circuit. So we're going to write down the differential equation. I already wrote it down here for you guys. We have negative IR for the voltage for the resistor, minus L di dt for the voltage from the inductor, and we have our usual EMF equals 0. So you can solve for the current as a function of time using this equation. Are there any questions about solving an RL circuit? Yeah, next slide. So yeah, you're gonna get that IT equals epsilon over R times 1 minus e to the negative RT over L. And this is very similar to the decaying functions we had for an RC circuit. If you graphed this, it would be like this. Your asymptote would be at epsilon over R. So this is I as a function of time. And you can also see the cases we talked about previously. At t equals 0, if you plug in t equals 0, you're going to get I equals 0 because the inductor is acting like an open switch in a sense. So it'll block the current, so I will become 0. But after a long time, as t approaches infinity, this equation gives us I equals epsilon over R. Because and you can see why, because the inductor will be like an wire, so you'll just have an EMF and a resistor, and that's just Ohm's law, I equals epsilon over R. Yeah, so are there any questions about that? If not, we can move to the next slide. Lucas, sorry about that. Yeah. So this is just the graphs I was talking about. Uh, this is voltage as a function of time. Wait, but yeah, this is voltage as a function of time. Um, and yeah, and one more important thing is that if you remember for the RC circuit, we define T as RC, and for this, we're gonna define T is L over R, because when you put that in, you can just write that as you can write your I of T and V of T as T over tau. So we're gonna define tau as L over R for our RL circuits. And yeah. Graphs in general are very useful for visualizing these circuits. And if you're taking like AP and stuff like that, sometimes they'll put like graphs and you have to analyze them or even draw graphs at times. Yeah. Next slide. So here's an example. This is a long one, so I'll give you some time to work on this, 5, 6 minutes. And yeah, message me if you have any questions or message me your answers if you get any. All right. I think we'll go over the first few parts maybe. So we have R1. I'll label these so it's easy for us. R1, R2, and R3. And we denoted the currents, we denoted the voltages. We have that this is our L. This is the L. So we're gonna close the switch and we want to find I1, I2, I3, and VL immediately after the switch is closed. So remember what I said? Immediately after a switch is closed in an RL circuit, an inductor like resists it. So the current through our inductor will be zero. This means that like the current through the third resistor will also be zero because like they're in series. So I L is zero and I3 is zero. And now we just have a loop. We just have a voltage, a battery, R1, R2, all in a loop. So now we just do our regular Ohm's law. We just say that um V over R1 plus R2 will equal our I will equal our I, where I is the current through a loop. And since they're in series, it's just I1 equals I2 equals this current. And if you plug in the numbers, V is 10, R1 plus R2 is 4 plus 4 is 8. You get that this is 1.25 amperes. Again, this is all for part A. All right, any questions about that? Oh yeah, and they asked for VL, so VL will just be 0 because I is 0. All right, so the next question, the next question asks for wait, oh no. The next question asks for the switch is closed for a very long time. Find I1, I2, I3, and VL. So I'll let you think about this, and yeah. Oh, also I misspoke for VL. VL is not 0. The VL will just VL will equal V2 since they're parallel, and V2 you can find using Ohm's law. So V2 equals I2 R2, which will equal 5 volts. Sorry about that. Yeah, and I'll give you like a minute or something for B. Okay, so for part B, the switch is closed and we went after a long time. So after a long time, if you remember what I said, the inductor just acts like a wire. So VL will equal 0. So it's just a wire, so we can ignore it basically. So we just have a regular DC circuit and you can solve this using like you can find REQ, right? REQ You can find that, and from that you can find I, which is V over RQ, and I will be, so you have I1, I3, and I2. So I will equal I1, but I2, but I1 will equal I2 plus I3. And you have another equation for the voltages. Um, V3 equals V2 since they're parallel. And you can like solve for everything using this, like all these equations I just wrote down. You can find Req from your parallel series formulae, I from Ohm's law, and I equals I1 equals I2 plus I3 from junction rule at this junction. And V3 equals V2 because they're parallel. And you can use Ohm's law to reduce this and relate I2 and I3. And with that, all of this, you can solve for I1, I2, I3. If you want to check your answer, the answer you should get is that I1 is 1.5 and I2, I1 is 1.5. I2 you should get 1.0 and I3 you should get 0.5. Are there any questions on part B? All right. Then let's look at C. For C, we have that the switch is then reopened and then find everything immediately after the switch is reopened. So I'll give you like 1 minute to think about this. Okay, I think I'll go over this now. So for part C, we have the switch is then reopened. Find it immediately after the switch is reopened. So remember inductor, it'll resist changes in the current. So immediately after the switch is reopened, the current will stay the same. It won't change immediately after. This is the same logic as when we put the switch on. The initial the current before the switch is turned on is zero, and after it'll be zero because the inductor will resist changes momentarily, like immediately after. So, and so that's the first thing. The second thing is that since we're opening the switch, obviously the current I1 will equal zero because it's just disconnected now. So we have I1 is zero, and we have that I, sorry, this is mislabeled. So then we have I3 stays the same. Um, I3 stays the same at 0.5 amperes. This is, that's a zero. And since it's just one loop, I2 equals I3 equals 0.5 amperes. And now the last thing we want to find is VL, voltage across the inductor. And for this we can use loop rule. VL minus I2 R2 minus I3 R3 equals 0. And with this, we can solve for VL, and you'll get, um, I think you'll get 6. Yeah, you'll get 6 volts. Are there any questions about that? All right. And the last part is that we have the switches reopened for a very long time. So after a very long time, the switch is closed, the switch is off, and it's a very long time. Find the I1, I2, I3, VL. I'll give you 1 minute for this also.
看那有多少学生？也都是学习比较烂的，对不对？学习不好的人才会来这儿，对不对？都是一些笨蛋才会，对不对？那你
Maggie,
跟
can
我
you
说
mute
你是，
yourself,
那
please?
只有烂学生才能烂这些。
Thank you. All right, yeah, I think we'll go over this now. So again, we have the same logic as previously. Since the switch is off, this left loop is entirely disconnected. So I1 is just 0. Moreover, um, after a very long time, as I told you previously, the inductor acts like a wire. The voltage across it will just be 0. And that's another bit of information. And then the last thing is that after a very long time, I2 will simply equal I3 will simply equal 0 because everything decays to 0. Everything, all the power dissipates. Um, yeah, all the current running will dissipate through the resistors, and there'll just be nothing left. So I2, I equals I3 will just be 0. All right. Are there any questions about that? This is similar to an RC circuit, right? After a very long time, your everything approaches 0. Everything decays to 0. Yeah. Um, yeah. And I think we finished right on time also. So if there aren't any questions, you're free to leave. Have a nice day.